Hey guys, welcome to part 2 of my series about regularization methods. In this part we will talk about the most famous and most known method, the so-called Tikhonov regularization method. Before we hop into the definition of this method, let's do a short recap. What do we want to solve? Well, at least what I want to solve. I want to solve the optimization problem you can see here, which contains of a quadratic term constrained by a linear PDE. In this form, we cannot tackle the problem directly, so we need to reformulate this PDE into a linear operator, which I call S. If you do not know how to reformulate this PDE into a linear operator, well, please watch my video. The link is, of course, in the description. Using this linear operator here, we can reformulate this PDE constraint problem into a more compact form you can see here. In part 1 of the series, we have taken a closer look into problems formulated like this, and the essence mainly was that such optimization problems are ill-posed. Meaning, if we have some noisy data in our measurement y, well, we cannot make any conclusions about the associated solutions x. This, of course, is a problem when you want to do some numerics. For instance, if you want to solve your PDE constraint optimization problem, you have to discretize your PDE using finite elements or, well, whatever your preferred method of discretization is. But this discretization introduces some noise into our measurement or into our optimization problem. Well, and there goes our stability, or in other words, we do not have any stability. So people have thought about this for a while and came up with several ideas. And again, the most famous is the Tikhonov regularization method. What are the requirements of this video? In contrast to my other videos, we will take a closer look into the proof or into some proofs, and therefore we will need some more advanced function analysis from our toolbox, namely, for instance, these weakly compact sets or weakly lower semi-continuity. So you should have seen, or you should have a solid understanding about weakly and weakly converging sequences. We will also need some more advanced optimization stuff, namely the Weierstrass theorem in Hilbert spaces. A small remark, I've written it here. This is only needed for understanding the proofs in full details. For an overall understanding, this is of course not needed, but if you want to take a closer look or if you want to fully understand the proofs, you will need some more advanced function analysis. Let's start with the existence of solutions. And the first problem we will take a closer look at is this following optimization problem here, this linear quadratic optimization problem. Therefore, we assume that x and y are some Hilbert spaces. Our set C is a non-empty closed and convex domain. And A, of course, is a linear operator between our Hilbert spaces. Under these assumptions, we know that this optimization problem here has a solution. And the proof is quite easy. Since C is a non-empty convex closed set, we know that it is weakly compact. And since the functional J, which is defined here, is of course continuous and convex, therefore it is weakly lower semi-continuous. By combining this lower semi-continuity with the property that C is weakly compact, we get the existence of solutions by applying the Weierstrass theorem. So, this is nice because we know that we have at least one solution. The question now which pops up is, well, which is the correct solution? And how to find this correct solution? And number 3 is, well, how do we deal with numerical instabilities? Let's talk a little bit about problem 1 and 2. I'm not a physicist, I'm a mathematician. But physicists usually, when they are minimizing some energy potentials and stuff like that. Don't pinpoint me on that. I'm not a physicist. But they always look for the solution with the minimal energy, meaning the solution which has a minimal norm in our space X. And keep this in mind, this will be important later on. And number 2 is, well, how do we find this minimal norm solution somehow, or the solution with the with the smallest amount of energy. And this is now governed by the idea of the Tikhonov regularization method. Now it's time to introduce the famous Tikhonov regularization, and the idea is to make the problem strictly convex by adding a strictly convex term, namely the norm of x, multiplied with some regularization parameter which is denoted by alpha. And here you can see the linear quadratic term we want to solve, and this is the Tikhonov regularization term. Before we start looking into some proofs and convergence result, I want to tackle the numerical aspects. Why is it a good idea from a numerical point of view to add this convex or the strictly convex term? And to do so, I want to go back to this unconstrained finite dimensional optimization problem. So now we're living in finite dimensions, no constraints. So this is quite easy. If we want to solve this problem here, we can just take a look at the first order optimality conditions, or take the derivative, and you end up with the so-called normal equation, which you can see here. So we know that if x bar is a solution of this optimization problem, well, it has to be a solution of this normal equation. And if you want to solve this normal equation, well, you are limited by the condition number of the matrix in front of x bar, which is A transpose A. Since A transpose A is a real symmetric matrix, it is a normal matrix, which means it commutates with its adjoint. And its adjoint is just here the transposed, and well, just basic numerical mathematics. And therefore we can take a look at the condition number of A transpose A, which is just the greatest eigenvalue divided by the smallest eigenvalue. Well, and this is just the fraction of the maximal and the minimal singular values of A to the power of 2. So what happens now if we do the same calculation for the Tikhonov regularization optimization problem of this optimization problem here? Well, to do so, we do a small reformulation. So we start with the Tikhonov regularization optimization problem. And this can, of course, be rewritten into this form here. And this now form resembles our linear quadratic form. Therefore, we can take the normal equation, which you can see here, multiply these matrix products, and you will end up with this normal equation here. Or just take the derivative of here if you're more familiar with derivatives of this functionals here. Just a small historical remark. This formulation, at least to my knowledge, first popped up in the 60s in the context of QR decomposition to stabilize this regularization here. So, if we now want to solve this normal equation here, or if we want to solve this, we are limited again by the condition number of this matrix here. And the condition number of this matrix here is, of course, just do a small calculation, it's just the singular values of A shifted by our regularization parameter alpha. And this is exactly how you can interpret it, or how to understand the Tikhonov regularization method in the final dimensional setting. You just shift the singular values of A away from 0. And of course, this gives you a huge numerical stability if alpha is bounded away from 0, right? I've written it here side by side. So here we have the unregularized optimization problem, and here you see the condition number. On the right hand side you have the regularized problem and the associated condition number. And you see, of course, that the condition number in the right hand side is smaller than on the left hand side. Meaning we are decreasing the condition number of the problem and, well, just making it more accessible and more stable for some numerical algorithms. This is just a small help to understand how the Tikhonov regularization works, at least in the finite dimensional setting. Why is it so common? Because it stabilizes some numerical algorithms by decreasing the condition number. Now it's time to go back to our infinite dimensional settings and take a look at the existence of our regularized optimization problem here. The setting is the same as before. We have some Hilbert spaces. C again is a non-empty convex closed domain. A is a linear operator. And for alpha greater than 0, this optimization problem here has a unique solution. The existence of solution follows by the same argument as before. We have a weakly lower semi-continuous function over a weakly compact set. And Weierstrass now gives the existence of solutions. And the uniqueness is a direct consequence of the strictly convexity of our function J alpha. And the strictly convexity is introduced by this Tikhonov regularization term here. So nothing spectacular here. In contrast to this unregularized problem, we now have a unique solution. So in the following, we will use the following definitions. They have been on the slides before, but I just want to pinpoint them here. So J is our unregularized optimization problem. J alpha denotes our regularized optimization problem. And we will need the so-called solution set of the unconstrained optimization problem, which is denoted by S. So S just contains all solution of this minimization problem here. And I already mentioned that physicists are sometimes looking for minimum norm solutions or solutions with minimal energy. And this now is formulated as the so-called minimum norm solution. So just take the element of S with the smallest norm, which of course is unique since X here is or make it X square is a strictly convex set, and well, then you get the unique solution X dagger of S if X is if F is of course non-empty, of course. And since our optimization problem minimized J alpha has a unique solution, which was just shown before, we denote the solution by X alpha. Okay, so much for the definition. Now I want to show you the main convergence result of the Tikhonov regularization in infinite dimensional spaces, and we are gonna prove this theorem here. Again, the setting is before. X and Y are Hilbert spaces. C is our suitable chosen set. A is a linear operator. And X dagger is the minimum solution. X alpha is the solution of the regularized problem. Then we know that if alpha goes to 0, we have convergence of X alpha against the minimum norm solution. So we have two strong results stated here in this theorem. Number one is X alpha converges to the minimum norm solution. This is not guaranteed by, why should this be guaranteed by some regularization term? And number two is, I want to focus on that, we are living in infinite dimensional spaces. So strong convergence or norm convergence is not guaranteed, of course. Usually you only get weak convergence, weak star convergence, and well, stuff like that. But here we get strong convergence. And this is, of course, a huge result or a huge argument for using the Tikhonov regularization, because norm convergence can be let me put it in perspective. If you're optimizing in finite dimensional spaces, weak convergence and strong convergence coincides. If you're in the infinite dimensional settings, they of course are completely different things. And just because you have weak convergence, well, your numerics can do weird things because you only have weak convergence, which is convergence in some weird spaces. But here we have strong convergence. So this is a strong result. And as I already mentioned, we're gonna prove this. The proof is not that hard. We have mainly everything at hand. We just need some nice arguments from function analysis, and we will split the proof into 3 parts. Number 1, we show that the sequence x alpha generated when alpha goes to 0 is a bounded sequence. If we have a bounded sequence, we can, in finite dimensional setting, extract a strongly converging subsequence. However, since we are living in infinite dimensional spaces, we can only extract a weakly converging subsequence. And but we can show, this is part number 2, that this extracted weakly converging subsequence is actually a minimizer, right? So we have x bar, which is the weakly limit of our subsequence, is actually a minimizer. We have to work a little bit for this. But this combining number 1 and 2 actually shows that our sequence x alpha converges against the minimum norm solution. This will be done in number 3. Okay, I think it's time to start with the convergence, with the proof, and we start with number 1. We start by using the fact that x alpha is a minimizer of j alpha. So we know that this inequality holds since x dagger is in our admissible set Z. So this inequality holds. And if we replace j by its definition, you can see the definition here. And if we now rearrange this terms a little bit, bringing x terms to the other sides and this ax terms on the other side, we will get this following expression here. And if you take a look at the right hand side, this now somehow looks like the definition of j without an alpha, right? And this is in fact what we're gonna use now. Here you can see the inequality we just derived again. We're now using the fact that x dagger is a minimum norm solution, or is a minimizer, in fact, of j. It's written here. So we know that j applied to x alpha is greater than or greater equal than j applied to x dagger. Or in other words, if you replace j by its definition, you know that this inequality holds. Well, but this inequality here is just inequality above here. Forget about the fraction here, this can be eliminated. So in other words, well, x alpha is less or equal than x dagger, and this holds true for all alpha. So just by rearranging some terms and using the fact that x alpha and x dagger are minimizer of j alpha and j respectively, we derived that x alpha is now a bounded sequence. So this now was quite easy. This finishes the part 1. We've showed that x alpha is a bounded sequence. So let's move on to part 2 of the proof. We extract a weakly converging subsequence, which is now possible since we know that x alpha is a bounded sequence, and we denote the subsequence by x alpha n, and the weak limit point is denoted by x bar. Now we do some estimates, and we take an arbitrary point in our admissible set C, and we start by using the definition of the weakly lower semi-continuity of our function j. Remember, j is a continuous and convex function, therefore it's weakly lower semi-continuous, and this is just a definition of weakly lower semi-continuity. So next step is we estimate this limes inferior by its limes superior, which of course is always true and always possible by the definition. We're still living on the subsequence here. And we now want to move on from this subsequence to the sequence x alpha. And this, of course, is possible if we are living in the world of limes superior, because we are just adding more elements to our set. Remember, the limes superior is the greatest cluster point of this sequence here. And of course, if you add more elements, we only get a possible bigger cluster point. So now we have made a step from x alpha n to our series x alpha. And the next step is needed for a small trick. We want to move from j to j alpha, which of course is again possible since we are adding a positive term. So we're making the terms or the elements in the sequence here bigger, meaning we can estimate the limit superior of j by the limit superior of j alpha. Now we have j alpha of x alpha, and we know that x alpha is a minimizer of j alpha. So we know the next step is that for any point in C, j alpha of x is bigger than j alpha of x alpha. It's just the definition or the property that x alpha is a minimizer. So this inequality here is true. And the next step is now take a closer look at the definition of j alpha. Well, nothing spectacular here. C is a bounded set, so the Tikhonov regularization term drops out in this limit superior, and we can actually there's an equality here. We know that this term here is less or equal than j of x. So what have we proven now here? We have shown that for any x in our admissible set, the function, the j evaluated at x bar is less or equal than j evaluated at x. Meaning, well, x is in fact a minimizer. The only thing we are left to show is that our limit x bar is in fact in our set C. But this is true since C is a weakly compact set. So this now shows that, this finishes the proof of part 2. We have showed that our weakly converging subsequence is, or the limit point of our weakly extracted subsequence is in fact a minimizer of our functional j. Now it's time to move on to the last part 3 of our proof, where we want to show that our sequence x alpha is in fact strongly converging to our minimum norm solution. We start by letting V be any arbitrarily weak limit point, meaning there exists a sequence alpha n such that x alpha n is weakly converging to V. By similar arguments as before, we can show that V is in fact a minimizer. And since the norm in X is weakly lower semi-continuous, we can directly conclude that the norm of V is in fact less or equal than the norm of X dagger. Here we make use of the fact that our sequence X alpha is bounded in the norm of X by the norm of X dagger. So this is a direct consequence here. We know even more. We know that X dagger is the unique minimizer of the norm in S. So this means by the uniqueness of X dagger, we can conclude that V is in fact X dagger. Or to put it in other words, X dagger is the only weak limit point of our sequence X alpha. Now we make use of the weak lower semi-continuity, the weakly lower semi-continuity of our norm in X, and conclude that the norm of X alpha, the limit of the norm X alpha, is in fact X dagger. And by standard arguments, we can now conclude that our sequence X alpha is in fact strongly converging against our minimum norm solution. And there we are. This finishes the proof. We have showed that our solution X alpha is strongly converging against X dagger. I know that we have made use of some deeper function analysis results, but I think the proof is quite nice and shows the properties and the possibilities of the Tikhonov regularization quite nicely. Now it's time to face some real-life problems, and with real-life problems I mean noisy data. So here again you have the regularized optimization problem, but now we only have access to a noisy version of our measurement B. I will denote this with B delta, and we assume that the following inequality holds. So we only have access to a version B delta, which is up to a absolute value of delta in the norm of y available. Can we find a suitable choice of alpha, which of course will depend on beta, such that the solution of the noisy version of the optimization problem, which I will denote, the solution will be noted by x alpha delta, is as good as possible, as close as possible. I put the good here in quotation marks because it's a priori not clear what is meant with good. But can we do some estimates, some stability estimates, some a priori estimates, stuff like that? Is such a thing possible? And the answer is, of course, yes, it is possible. And I want to start with some stability results. Again, we have x alpha and x alpha delta, the noisy solution of the optimization problem here. And then we know that the following stability estimate holds. So the solution x alpha and x alpha delta are as close as possible up to a fraction of 1 over square root of alpha. So this means, what does this mean? First of all, this means we do have stability. Point. This is good. This is good. However, the smaller alpha gets, the more unstable this Tikhonov regularization becomes. And with unstable, I mean numerical artifacts will appear and we will see the impact of some noisy data. And this scales, of course, with delta, but the problem here is alpha. Because sometimes you have to choose alpha really small in order to get a good result. But then you will run into instabilities issues. So you have to be carefully here and have to balance your alpha in order to find a good path between noisiness or control of the noisiness and control of the stability. If you have this result at hand, you can easily construct an a priori estimate how to choose your alpha in order to get a good result. This is part of the next theorem. If you choose alpha in the following way, that if the noise goes to 0, your alpha should go to 0. Okay, this is clear. And furthermore, the fraction of delta power to the power of 2 divided by alpha should also be 0. If these two properties are satisfied, then you know that first of all the states converges, so ax alpha delta minus ix dagger goes to 0, and we even know more. We even know the conversion speed. We know this goes with O of delta. And most important, we have again strong convergence. The proof of these two results are quite easy. Just take the first order optimality conditions. When we go back one slide, we have two optimization problems here, one with B and one with B delta. Just take the first order optimality conditions. Since we have additional constraints here, we have a variation inequality, but just add them. We have Hilbert spaces, so we have scalar products available. Just add them, play around with terms a little bit, and you will easily end up with estimates like this. Okay, so it's time for a short summary. What properties do the Tikhonov regularization has? First of all, I've showed you that the regularization term, first of all, stabilizes the condition number. Okay, I've only showed it you in the finite dimensional setting. But this allows to construct numerically stable algorithms which solve the first order optimality condition. I have showed you this second part here. This I have showed you in the Hilbert space setting, that the sequence x alpha converges strongly. I cannot focus this enough. Converges against the minimum norm solution. So physicists are happy here at this point, and the mathematician is happy because he has strong convergence, so everybody is happy. Perfect. And I showed you that the Tikhonov regularization is capable of dealing with noisy data, and you can also construct some a priori parameter choice, how to choose your parameter alpha depending on the noise. Of course, there are still some open problems, and I want to finish this video with some open questions. I've already pointed this out a little bit. How do we deal with issues like stability or numerical issues if the regularization parameter alpha is very small? Well, maybe you have to construct some suitable algorithms, like something like iterated Tikhonov or something like this. Maybe this is part of the next video, we'll see. The next question is, can these results somehow be extended to nonlinear operators? Up to now, we have only dealt with linear operators. Our motivation was that A is the solution operator of a linear partial differential equation. What happens if you go to a, let's say, a semi-linear partial differential equation? Then the solution, reciting a solution operator, okay, it exists, this is nice to know, but it is nonlinear. So what do we do now? And more like numerical aspects here, if we have a solution operator of a partial differential equation, how do we implement this in an efficient way, of course? Up to now, we have only abstract this operator and work with the operator itself. But what about numerics? What about implementation? And number 4, what about conversion speed results? Can we impose some conditions on our minimum norm solution such that we can show some conversion speed results? Well, these are open questions, and we will tackle some of them in the next part. Up to now, I will finish this video now. Thank you for staying with me. Thank you for being interested in this topic of regularization method, and have a nice day and see you around.